In this episode, we're going to focus on one of the most common ways organizations accidentally leak information in the cloud. They expose stored data without meaning to, often through tiny permission choices, mishandled keys, or slow configuration drift that nobody notices until it hurts. When people first hear cloud data exposure, they sometimes imagine a dramatic hack where an attacker breaks in through a complex technical trick. More often, the reality is simpler and more uncomfortable. The data was placed somewhere it could be reached, and the protections around it were either missing, misapplied, or gradually weakened over time. For a brand new learner, the most important mindset is that cloud storage is not automatically private just because it feels like a personal folder or a company drive. In cloud environments, storage is more like a building with many doors, badges, spare keys, and contractors coming and going. And your job is to make sure only the right doors exist and only the right people can open them. By the end, you should be able to explain why permissions, cryptographic keys, and drift are connected, and why controlling exposure is more about disciplined habits than heroic last-minute fixes. A useful place to begin is by clarifying what we mean by cloud storage and exposure in everyday terms, because misunderstanding the basic model creates most of the preventable mistakes. Cloud storage usually means a managed service where data objects, files, or database records live on infrastructure you do not physically own, but you can still control how it is accessed. Exposure means that data becomes reachable by someone who should not have it, whether that is the general public, another customer, another internal team, a vendor, or even an attacker who steals credentials. Notice that exposure does not require the data to be copied. Sometimes it is enough that it can be read or downloaded. Exposure can also happen without anyone intending harm, such as when a developer makes a resource accessible for testing and forgets to undo that change later. In security, intent does not change the outcome, so we treat accidental exposure as a serious event because it produces the same result as a deliberate breach. This is why cloud security leadership focuses so much on preventing the easy failures, because the easy failures are the ones that happen at scale. Once you understand that exposure is often about reachability, you can see why permissions sit at the center of the problem. Permissions are the rules that decide who can do what to a resource, like read a file, write a new object, delete a record, list what exists, or change settings. In cloud environments, permissions often come from identity and access management, IAM, which connects identities like users, services, and roles to allowed actions. When permissions are too broad, you get overexposure, and when they are too narrow, systems break, so people start adding shortcuts. Beginners sometimes think of permissions as a single switch labeled public or private, but the reality is layered and detailed. You might have a rule that allows a service to write data but not read it, or a rule that allows reading but only from a particular network location, or a rule that allows listing names but not fetching the content. These details matter because attackers love permissions that are slightly too broad, since they can chain them together into a path from a small foothold to a major data spill. A related beginner trap is assuming that internal equals safe, because in cloud systems the boundary of internal is not always what you think it is. If a storage resource is reachable from the internet, then the internet is part of the boundary, even if you intended it to be internal. If a resource is reachable from another account or project, that is also part of the boundary. If a resource is reachable by a service identity that is used by many applications, then every one of those applications becomes part of the boundary too. Cloud systems are built for sharing and integration, which is useful, but it means you must be explicit about who is allowed in. The practical lesson is that you reduce exposure by minimizing who can access storage and minimizing what each identity can do, which is the principle of least privilege. Least privilege is not a slogan. It is a design choice you implement by starting with minimal permissions and only adding what is truly necessary, rather than granting everything and hoping nothing bad happens. Another concept that ties directly into storage permissions is how authentication differs from authorization, because new learners often blend these together. Authentication is proving who you are, like showing an ID badge, while authorization is what you are allowed to do after you have proven who you are. In cloud storage exposure incidents, the attacker often does not need to defeat authentication in a clever way. Sometimes they simply find a storage location that does not require authentication at all. In other cases, They obtain valid credentials through phishing or reused passwords, and then authorization rules determine how far they can go. If authorization is too permissive, one stolen account can lead to reading large datasets or changing protections. If authorization is well-scoped, the same stolen account might only access a small, low-impact area. This is why security leaders push for role-based access and separation of duties, because those approaches reduce the blast radius when the inevitable credential problem occurs. Now we need to bring cryptographic keys into the picture, because keys are another layer that controls access, and mishandling them is one of the fastest ways to turn private data into exposed data. A cryptographic key is a secret value used by encryption systems to lock and unlock data, and it is not the same as a password, even though people treat it that way sometimes. You can think of encryption as the lock and the key as the only thing that can open it, but in cloud systems there are many variations, like keys for encrypting stored data, keys for signing access tokens, and keys for establishing secure connections. When cloud storage is encrypted, the data may be unreadable without the key, which sounds like a perfect solution, but it only helps if key custody is handled carefully. Key custody means who controls the keys, where the keys live, how they are rotated, and who can use them. If keys are stored in the same place as the data, or embedded in application code, or shared widely across teams, then encryption becomes a comforting label rather than a meaningful control. It also helps to understand that cloud services often offer encryption by default, but default does not mean the risk is fully addressed. Many platforms encrypt data at rest automatically, yet exposure still happens because the permissions allow someone to request the data in plain text through legitimate service calls. Encryption at rest is meant to protect against certain threats, like a physical disk being stolen or a low-level storage component being accessed, but it does not prevent an authorized caller from reading data. If the authorization is too open, the service will happily decrypt and deliver the data to whoever asks, because from its perspective that is the correct behavior. This is why permissions and keys must be considered together, not separately. Permissions govern who can request data operations, and keys govern whether data is protected outside those operations. A strong design uses both: tight permissions to prevent improper access requests, and strong key management to ensure data remains protected even when infrastructure is stressed or compromised. Key management also matters because keys can quietly become shared secrets that spread across your environment, and once that happens, exposure becomes difficult to contain. Imagine a team uses one encryption key for many storage locations because it seems convenient, and that key is used by multiple applications. If that key is ever leaked, you suddenly have a multi-system incident because the same key unlocks many datasets. Rotating that key becomes disruptive because you have to update every system that depends on it, and that disruption is exactly why teams avoid rotation, which creates long-lived keys that are more likely to leak over time. A healthier approach is to keep keys scoped appropriately, rotate them on a schedule, and restrict who can use them through policy. Even at a beginner level, the lesson is clear. A key is not just a technical detail. It is an asset that needs ownership, protection, and lifecycle management, because it is a direct path to data. At this point, it's useful to connect these ideas to the real-world patterns that cause exposure in cloud storage, because the patterns repeat across providers and services. One common pattern is making a storage location publicly accessible to share something quickly, then forgetting that it remains public. Another pattern is granting broad access to a service identity because an application needs to work. Then that identity gets reused for other applications, and the permissions no longer match the original purpose. A third pattern is misconfigured access policies that unintentionally grant access to a wider group than intended, such as a whole organization when only one team needed it. There are also patterns involving backups and logs, where data copies are stored in a secondary location that is less protected than the primary system. Attackers look for these weaker copies because they often include sensitive information and are not monitored carefully. When you recognize patterns, you stop thinking of exposure as an unpredictable event and start treating it as a predictable outcome of specific mistakes. This leads directly into configuration drift, which is the slow, often invisible shift away from a secure intended setup over time. Configuration drift happens because cloud environments are dynamic, teams deploy updates, adjust settings, add integrations, and respond to incidents by making emergency changes. Each change might make sense in isolation, but the cumulative result can be a system that no longer matches the secure baseline you thought you had. Drift can also occur when a new service is added with default settings that are more open than your organization's standard, or when a policy is copied from another project without fully understanding it. Beginners sometimes picture configuration as a one-time setup step, but in cloud systems, configuration is more like ongoing gardening. If you stop tending it, things grow in unexpected directions, and your environment becomes harder to understand, which makes exposure more likely. To control drift, you need the idea of a baseline, which is a documented and enforced starting point for how storage and access should be configured. A baseline answers questions like whether storage should be private by default, what logging is required, what encryption settings are mandatory, and what types of identities can access certain data. Baselines are not meant to be perfect. They are meant to be consistent, so you can detect when something deviates. When you have a baseline, you can run checks that compare current configurations to expected configurations, and you can treat deviations as events that require explanation. The key concept for beginners is that drift is not a moral failure by engineers. It is a natural consequence of change. The goal is to build systems that make secure configurations easy to maintain and insecure configurations easy to detect, so drift becomes a manageable operational risk rather than a surprise crisis. A subtle but important part of controlling cloud data exposure is understanding that permissions and keys are often managed by different people or teams, which can create dangerous gaps. For example, one team might set storage permissions, another team might manage keys, and a third team might deploy applications that use both. If these teams are not aligned on the sensitivity of the data, you can end up with a mismatch where data is highly sensitive but protected only by casual access rules, or where data is encrypted but keys are accessible to too many identities. This is why leadership-level thinking emphasizes ownership and accountability, even for technical controls. Someone must be responsible for deciding who should access a dataset, what protections are required, and how exceptions are handled. Without ownership, the environment becomes a collection of reasonable individual choices that add up to unreasonable systemic risk. It also helps to address a misconception that sometimes appears in beginner conversations: the idea that if data is inside the cloud provider, the provider is responsible for keeping it safe from exposure. Cloud services follow a shared responsibility model, where the provider is responsible for certain layers, like physical infrastructure and core service security, but the customer is responsible for configurations, permissions, and access management. This means the customer decides whether a storage location is public, which identities can access it, and how keys are used. When exposures happen, they frequently happen within the customer's responsibility area, not because the cloud provider failed at their job. The practical takeaway is not to blame the cloud, but to accept that cloud security is about making good decisions with powerful tools. The cloud makes it easier to build quickly, but it also makes it easier to expose things quickly, so your control systems must match that speed. As we move toward pulling this together, it's valuable to think in terms of prevention, detection, and response, not as a checklist, but as a mindset for controlling exposure. Prevention means designing storage so it is private by default, granting minimal permissions, and treating keys as high-value secrets with strong custody. Detection means continuously looking for changes that create exposure, like new public access rules, expanded permissions, disabled logging, or key usage that does not match expectations. Response means having a plan for what you do when exposure is found, including how to restrict access quickly, rotate keys if needed, and assess what data might have been reachable. Even for beginners, this triad is a good mental model because it keeps you from relying on a single control. In real environments, you assume that mistakes will happen, so you build layers that catch mistakes early and limit the damage. Finally, it's worth reinforcing how all three ideas in the title fit together in a single story, because that story is what you will remember under pressure. Storage permissions decide who can request access to data, and mistakes there can instantly create exposure. Keys and encryption decide whether data remains protected outside normal access paths, but they only help if key custody and usage are tightly controlled. Configuration drift is the slow process that turns a secure design into an insecure reality, often without anyone noticing, and it can affect both permissions and key settings. When you control cloud data exposure well, you are not doing one heroic action. You are creating a steady system where secure defaults are normal, broad access is rare, keys are treated with respect, and drift is continuously checked. That combination is what keeps data from quietly becoming public, and it is what separates a cloud environment that merely functions from one that can be trusted.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.